Hello, this is Brock Lemires, and we are continuing our study of embedded systems design. In this video, we're going to start looking at the anatomy of an assembly program file, and this will gear us up toward actually typing in our first program. The syntax we're going to be looking through is somewhat generic across all assembly language programming tools, but this one is going to be specific to the Code Composer Studio software provided by Texas Instrument, specifically targeting the MSP 430 FR2355 Launchpad board. I know that's a lot, a lot of numbers, but it's the red Launchpad board that we're ultimately going to be programming. Okay, so let's take a look at some of the basics. We are going to name our files .asm when we create a new program code. Okay, so main.asm is going to be almost always what we do in this book. This is just the same as if you were writing in C, you'd say main.c. We're going to do main.asm, and that's how we indicate to the tool that we're programming in assembly. And then in terms of terminology, when you develop your program, we're going to start in assembly. Every line in the assembly source file can obviously be empty, but anything that isn't empty can either be an instruction line, a comment line, an assembler directive, or a macro invocation. And so we specifically care about the first three of these: instruction statement or instruction lines, comments, and assembler directives. Macro invocation is a little bit more advanced and something we won't get to. And so the terminology we use is we call a line that is not empty a statement. Okay, so that's what we want to say. So what kind of statement are you typing out on this line? And you say, well, it's an instruction statement, or it's a comment statement, or it's an assembler directive statement. So that's the terminology we use. Let's start with the big one, which is instruction statement. So this is what you usually think of when you think about programming and assembly, is where you drop down opcodes and operands. And the difference of programming in assembly versus programming in binary would be is really two or three different things. It's one, instead of writing the binary code for the operation code of an instruction, you use its mnemonic. And so you'll see here as an example, you'll see like MOV and DEC for decrement and JNZ. You don't have to know what any of those mean at this point. It's just that you know that these mnemonics exist for every instruction. The other thing that this programming and assembly gives you is the ability to, instead of saying, put this move opcode and operand at address 8000, it allows you to just code in the program file and allow the linker and the compiler to actually put it into memory at the right location. And we'll see as we start looking at address labels that becomes very, very nice for us, because keeping track of the addresses is kind of a pain. And then the other thing that allows you to do, of course, is give comments, but then it also allows you to have directives that tell the assembler information about your program, about like, what is this? Are these statements? Are they program code? Are they variable allocation, et cetera, et cetera? So the instruction statement is going to be where you actually put information, or you're going to code up an instruction, and every line of an instruction statement is a actual instruction that will be inserted into memory. The instruction statement is divided into 4 fields. You have an address label, a mnemonic field, operand, and an operand list, and then a comment. So these are the 4 fields of an instruction statement. So let's walk through each of them. Address labels. So an address label is a way to mark an address or a point in the program that can be referenced by other instructions. So imagine that you're creating like a main loop, and you want to do some instructions, and then you want to tell the program, go back up to this location. Okay, you don't want to have to like actually grab this hard-coded address and say, I'm going to go to address 8000A, put these instructions, and then when I get down here, take the program counter and move it back to 8000A. That would be almost impossible to program. I mean, people have done it in the beginning of computers, but we don't do that anymore. So what we do is we use labels, and a label allows us the ability to do a couple things. Number one, it gives control of where this address is actually physically located in memory. It gives that control to the assembler, but it marks it for us. So now if I put, for example, this loop right here, I can reference that from, let's say you have an instruction that's going to move our program back up to loop, you can use it right here. And I didn't even need to care really about what the absolute address was of loop. Okay, so it allows me to mark these locations. Now, this is great. The way that you put an address label in there is it has to be the first column. So anytime you type any text in the first column, which means there's no white space to the left of your character, the assembler will interpret it as a address label. Okay. You can put an optional colon after it, and the colon is not part of the label. So for example, I put loop colon and I referenced that address label down here. I didn't put the colon right here. The reason the colon is nice is because you don't need it, it's optional. But CCS will actually recognize the colon and say, oh, this person is putting in an address label, and it'll color code it for you. So notice in this example, it's kind of a red. That's because I put the colon there. If I didn't put the colon, it would just be like black. So it's just a graphical thing. So that's what an address label is. The second field is the mnemonic, and the mnemonic is the word that describes the instruction. So a move instruction has a mnemonic of MOV. A decrement instruction has a mnemonic of DEC. Where do you find these mnemonics? Well, you find them you can look in my book because I wrote them all down in there for you, but you can also go to the data sheet. And now this is the question, which data sheet? There's 3 data sheets we talked about. Is it going to be in the Launchpad data sheet? No, that just describes the peripherals that describes the I/O on the red board. Is it in the device-specific data sheet? You'd think so until you realize that device-specific data sheet is for a specific part within the MSP 430 family. So the mnemonics are going to be found in the family data sheet, the one we call the monster, the 600 plus page one. But anyway, you put these in there, all of them are recognized, and they have to have white space before them. So the assembler looks and says, oh, I see white space and then I see a character. That is going to be treated as a mnemonic. So the first character after a white space. This is usually where you tab them over. You know, it can be one white space if you want your program to look horrible, but you usually tab these over and kind of align them so that it's real distinct. It's like, oh, I'm in this column and that is a mnemonic. Okay, so that's what a mnemonic is. And it's just a descriptive name for the instruction. And let's see, the next field is the operand. Some instructions require an operand. An operand is additional information that might be needed by the instruction. For example, a move instruction, it's like, what are you moving? You got to give it what information is to be moved and where it's going to go. So this instruction requires an operand. So the way you give an operand is that the assembler sees the instruction and it knows, oh, this particular instruction needs an operand. So then the operand is listed after white space following the mnemonic. Again, it can be one space, but it looks horrible. So you usually tab it over. So a typical assembly file, you'll start seeing these columns where it's like, over here is address labels aligned to the left side of the page. Then this column that's tabbed over is going to be all your mnemonics. And then you're going to tab over and you're going to have all your operands, if they have operands. And then over here will be your last field. Some instructions require more than one operand. For example, you know, a decrement. That only requires one operand. It's like, I'm going to decrement something. What's the something? Well, R4. So I'm going to decrement register 4. They'd only required one operand. But a move, you need to provide a source and a destination. So what you do is they're listed comma delimited. And you actually don't need, you can actually not have space if you want, but you always do put space so it makes it more readable. So an operand is basically, yeah, it's additional information that is provided for the instruction. All right, and then we get to finally the comment. Comments are just like comments in any other program. They just give information about they just document your code. The way that you do this in CCS is you use semicolon. When you put a semicolon, CCS will recognize that as a comment, and everything after it, it will turn green, and it's a line comment. That means that there's no wrapping on here, so you have to put a semicolon after, or you put a semicolon for each line that you want to be a comment. Again, you typically tab align these over here so you can see these distinct 4 fields aligned. And comments can absolutely be on their own line. So like we talked about being an instruction statement. Well, you can also have a comment statement if you put this at the beginning of your line. And you'll see that in this example right here when we move to assembler directives. So right up here, notice that I had, I wanted to make like a little header. So I just put semicolons and it turns it green and everything's great. Okay. The next type of statement is an assembler directive. And an assembler directive is something that you need to tell the assembler information about your program, but it's not an instruction. Okay, so an example of that is you say, I am going to write some instructions, but I want you to take these instructions and put them in a particular portion of the memory map. You need a way to tell the assembler that. And so you do that with a directive. Another example would be you're going to type in statements in your program file, but they're not instructions. You might want to set up some variable space in data memory. Well, you have to have a way to tell it that, so you use directives in order to tell the assembler what you're trying to do. This is an example of a file that's coming together. This won't work if you type in this program, so don't type this in. But this is an example of what you might want to do. So for example, let's say you needed to tell the assembler that this part of my program file needed to go into program memory. You would use an assembler directive that's called .text. If you wanted to set up some variables and put them into data memory, just reserve some information, reserve space basically, you could use the .data directive. So that's how we tell it additional information. Details. Directives start with a period. So if you put a period and then you type in a keyword that's recognized, it'll turn this like purple. So CCS recognizes that. They also are aligned in the mnemonic column. So that's kind of how you keep your, that's how you keep the thing organized. And like I said, you can use it to allocate, to move stuff within program memory, allocate variable space, and you can also use it to set up constants and manage global variable access. There's a lot of directives that exist. A lot of them we're not going to use. Some of them are automatically populated into the assembly code that we'll see later, but they're a critical part of this. All right, and like I said, yep, okay. Let's look at some of them. Now, again, where do you find directives? The first place to look is the book. Okay, so what I did is I went through this big PDF provided by TI, and I tried to strip out the most critical assembler directives that we'll use in here. And there's some that we actually don't use, but I tried to format them into a concise table. And so I have, I think, 3 tables in here that kind of give you the main ones, okay? And this is all we'll use, okay? I mean, if you needed to know where, you'd have to go out to TI and look at Google like assembler directives, and it would give you a document. But these are defined by CCS, okay? These aren't something that I made up, and they probably aren't portable to other design environments. These are specific to CCS. Okay, so let's look at, you have some to control memory use. So you have ones that are like .text and .data. They tell you this portion of my file is going to go into program memory. This is going to go into data memory. They have some retain refs. These are interesting ones. The assembler is very clever, and sometimes you'll type in code and it'll recognize that your code doesn't ever access the outside world, and the assembler will say, that's stupid, and it'll just remove it. And so then you go and you're trying to step your program and look at the instruction execution, and the instructions are gone. And we'll see this when we're trying to just figure out how to do data manipulation instructions. The assembler removes stuff, and so you can actually say, hey, please just leave my code. I'm trying to play around with it. This isn't a real program. So you could have ones that do that. Then you got ones that can reserve reserve sections, name sections. You can reserve uninitialized data memory sections. So those are the main ones for memory control. You also have a whole bunch which are used to reserve or initialize variables. These are very handy. If you want to set up a variable, you use .space. And also, let me just tell you, you're not going to understand any of these as I talk through them. I'm just trying to give you an overview of that they exist and that there is a table that has them listed, and you really learn them when you start typing them in. But for example, if you wanted to reserve, let's say, a word in data memory to use as a variable later and it wasn't going to be initialized, use dot space. If you wanted to initialize constants either in data memory or in program memory, you use all of these directives: dot byte, dot short, dot long, dot char, dot string, dot c string, float, double, and yeah, and so that's how you do it. Those are the directives. Let's take a look at variables. Typically, you can have a variable in data memory that's either initialized or not initialized. That's the difference between like dot space and dot byte. Constants, I said you can put constants in data memory. It's kind of interesting because you think about a constant, usually you would say my data memory is where everything is going to be allocated and my program memory is reserved for instruction statements. And it turns out not necessarily true. If you have a constant that you absolutely are not going to change, you might as well put that in program memory, because then it's going to be in non-volatile memory and it won't use up your data memory. Remember, program memory is usually bigger than data memory. So we have 32K of data memory on this MSP we're using, and we only have a couple K of data memory. Okay, so anyway, here's some examples of how you might set it up. Again, we'll be doing examples of this and actually coding it and looking at it in memory, so you don't need to understand this. But it just shows you like dot byte. You can see that you can reserve a byte and put 3F in it. Notice that the syntax for hex, you put a little H after it. Here's an example of syntax where you have AB is what I'm going to reserve, but oh no, it interprets A as like you're trying to set up some label or some identifier, and it's like, so in order to tell it that it's going to be used as a number, you put a 0 in front of it. So anytime you have a hex character as the leading character, you have to put a 0 in front of it, and you'll get used to that because that is going to be a lot of errors for you, a lot of compile errors. That's all right. And you can put characters in there, tick separated, tick, just like in C, strings or double quotes. Yeah, and then float. Float is a floating point number. Double is a floating point number also, but twice the memory allocation. So that's an example of it. And then finally, you have some that are for information interchange between multiple files. So for example, if you're going to have, this is especially important when you think about like the linker, right? The linker has labels of sections of memory that you're going to try to tie into. So you need to have global symbols that are used between files, and some of these you put in, some of them you don't. If you happen to develop a program that's so big you need multiple assembly files, then you need to share the variables between the files. Assembly makes you be very explicit about saying, I have a variable in my file and I want it to be used in another file. So you have these .def and .ref. So the two files will actually want to be saying, I have a variable here that needs to be used in another file. And then in that file, you'll have to put, hey, I'm using a variable name from another file. So, I mean, it really locks the rules down so that you don't accidentally have the same variable in two files and they are used and you didn't mean to do it. Okay. And then let's see, this .decls is interesting. It allows programs, we'll actually use this, it allows programs to use a mixed environment. And mixed means you can have some source files that are assembly and some that are also C. The reason that's critical is because think about the linker and the memory map. Somebody had to go in and create a program that described all the memory locations. And they did that in C. And that's fine, as long as we allow the design environment to read in both assembly and C, we can program in assembly. Okay, so those are the key ones. Yeah, so globally, that's basically everything I just said. Here, going back to our example, you can kind of see the entire thing coming together. You've got comment blocks here. You've got, for instruction statements, you've got your 4 fields. You've got label. You've got mnemonic. You've got operand. You've got comments. Notice that an address label, if I put a semicolon, it's great. Down here, oh, forget that little guy. I drug this a little bit too short, but anyway, and then you can see the directives down there, and you can see I'm using directives here, and we put the directives aligned with the mnemonic column. Some final syntax, just miscellaneous. We use the term identifier to represent labels, registers, symbols, anything that needs a name. So for example, if I said R4, that is register 4 in the CPU. I would say that R4 is an identifier. If I had an address label that was called main loop, I would say that main loop is an identifier. And it's basically just a technical word for assigning alphanumeric characters to a label, okay? And yeah, you can have capital letters, lowercase letters, 0 to 9, and also underscore. You can't have anything else, okay? So basically the names of things are called identifiers. First character cannot be a number though, okay? It cannot be a number and it cannot contain embedded blanks. So it has to be a continuous chunk of characters. And it is case sensitive. This is going to kill you, but we'll go through it together. Case sensitive. Identifiers are case sensitive, but other things are not case sensitive. So let's take a look at this. Sections. All a section is a block of code that can be occupied by a continuous space and memory map. An obvious section is something like a data memory. That's a section. Program memory is a section. And again, there's directives that help kind of allocate our code into these sections, but it's good to know the term section because when you go look at some of the documentation that you'll be like, what is this section thing? Okay, here's the big one that's gonna get you. Case sensitivity. CCS is not case sensitive on mnemonics. So capital MOV is the same as lowercase MOV. Whatever, that's great. But identifiers are case sensitive. So capital main is not equal to lowercase main. And you'll be getting all these compile errors and you're gonna bang your head against the keyboard. And it's just, that's the way it is. Identifiers are case sensitive and everything else is not case sensitive. So if you just kind of have heard that before, then it'll help you kind of resolve some of the compilers that you're gonna get. Okay, so that's an overview of basically the anatomy of an assembler program. And this is gonna set us up to actually start coding. So remember, subscribe to my channel so you're always up to date on the latest videos.